The subject of today's lab is Charles's law. Charles's law says the volume of a gas is directly related to its temperature. Another way of thinking about it is if you increase the temperature of a gas, then its volume will increase. Conversely, if you decrease the temperature of a gas, its volume will also decrease. Everybody write down faucet, F-A-W-C-E-T-T. It's really very easy to demonstrate Charles's law. Let's take a look at this demonstration I did in the lab. All right, what we're going to do is we're going to take a look at a balloon that has been placed in a freezer. I filled the balloon up, put air from my lungs in it, and have left it sitting inside my refrigerator slash freezer for several days. So let's take a peek on our balloon here. Look at my balloon. You can see already it's got a little dent in there, right? Because it's got so little air in it. And if you just look at how big it is, it's not really that big at all, right? Okay. Now let's warm up this balloon. Now, according to Charles's law, as we warm this balloon, it should get bigger. As a matter of fact, I can feel it getting bigger in my fingers here. And what I've done is I've placed my balloon in some hot water here. And hopefully in a few minutes, what we're going to see is it getting much larger here. Exciting. Groundbreaking television. Yeah, this video will beat all those Minecraft videos out there. Said no one ever. Alright. Let's switch to a little time lapse here. I'm back, and our balloon has clearly grown. As we increase the temperature of the gas inside our balloon has grown very, very dramatically. Not only that, but because the volume's increased and the mass of air inside the balloon has stayed the same, you'll notice the density of our balloon, the density of the gas inside our balloon has become much, much lighter. Now our balloon barely fits inside here and pretty much fills the mass of the size of the container. Remember, when we had it in that refrigerator, that balloon was about 3 inches when we looked stem to stern, so to speak. And if you're looking at that balloon now, it's hard to see, but it's grown about a good 2 inches there. So you can dramatically see the effects of Charles's law. As you increase the temperature of a gas, you increase its volume. Plus, who else gets to say that they went to class today and they boiled balloons? Write down Kate Jackson. Write down Kate Jackson. Now, Charles's law is a little bit deceptive in terms of how we would use it in our everyday life. And that has to do with temperature scales. Now, in our everyday life, we look at temperatures in degrees Fahrenheit. In the lab, we look at temperatures in degrees Celsius. One thing you'll notice right away about those temperatures is the mathematical relationship looks a little bit odd. For example, our body temperature is 98.6. In Celsius, the human body temperature is 37 degrees Celsius. Even more clearly, and what we really want to talk about here, is let's look at the boiling point and freezing point of water. In the Fahrenheit scale, you may be familiar with the fact that water boils at 212 degrees Fahrenheit. On Celsius scale, it boils at 100 degrees Celsius. Water freezes at 32 degrees Fahrenheit, but 0 degrees Celsius. Something is clearly askew with these two temperature scales. Not only that, but both temperature scales have a problem when it comes to volume. We just said, according to Charles's law, there is a direct relationship between volume and temperature. Because that relationship is direct, if we have 0 volume, we should have 0 temperature. However, on the Celsius scale, at 0 degrees Celsius, do we have 0 volume? No, we don't have 0 volume. Matter of fact, we have quite a few things with volume at 0 degrees Celsius, right? If it's the freezing point of water, we know that ice cubes have volume at 0 degrees Celsius. Therefore, a relationship between volume and degrees Celsius is not mathematically valid. Same for Fahrenheit. At temperatures of 0 or less on the Fahrenheit scale, we still have volume, right? Recently, just here in Kentucky, about 2 or 3 years ago, we got the temperature to negative 12 degrees Fahrenheit, and none of us ceased to exist, right? We were all still around. So clearly, objects can have volume at both 0 degrees Fahrenheit and 0 degrees Celsius. So there's something mathematically wrong with the relationship between Fahrenheit and Celsius when it comes to Charles's law. There is a third temperature scale, and that's the Kelvin scale. And the Kelvin scale is the only temperature scale where Charles's law works. The Kelvin scale is a scale designed and set so that you have 0 Kelvin. Kelvin scale is a scale designed so that when you have 0 volume, you have 0 Kelvin, right? Creating a mathematically valid relationship. Because if volume and temperature are directly related, when you have 0 of one, you should have 0 of the other. Therefore, since you can't have less than nothing, 0 Kelvin is the coldest temperature possible. Therefore, it's referred to as absolute zero. Scientists at the University of Chicago, that's the one that I hear about most often, constantly are working at making colder and colder temperatures. And whenever they make a colder temperature, guess what they do? They redefine what that zero is. Every once in a while you'll see a big news article that will say that somebody's come up with a temperature colder than 0 Kelvin. Well, in that case, what do? They redefine what 0 Kelvin is, or they're dealing with an area of theoretical physics, one of the two. But at 0 Kelvin you have zero volume. Therefore, it's referred to as absolute zero. Now, I hope everybody's okay with that concept. Now, the relationship between Kelvin and Celsius is really simple mathematically. Mathematically, come on, cooperate with me. Your temperature in kelvins, and we never say degrees Kelvin because Kelvin's an absolute scale, so it's never degrees kelvins, it's just kelvins. Your temperature in kelvins is equal to whatever your temperature in Celsius is plus 273.2. So 0 degrees Celsius would have a temperature of 273.2 kelvins. Water on the Celsius scale boils at 100. On the Kelvin scale, it would boil at 373.2 kelvins. Your body temperature in kelvins would be 37 degrees Celsius plus 273.2 equals 310.2. Charles's law is better thought of as the volume of a gas is directly related to its temperature in Kelvin. Any other temperature scale will create a deception or won't create a realistic situation. Now, I've always tried to avoid making this class too math intensive, but in order to thoroughly discuss why Kelvin is so important, we really need to look at the mathematical formula for Charles's law. Charles's law says in terms of a mathematical formula that the volume final of a gas is equal to its initial volume times its temperature final divided by its temperature initial. With this formula in mind, let's look at the importance of temperature. Let's consider the following very simple scenario. I have a balloon. Come on, cooperate with me. My program is being hinky today. I have a balloon and its volume is 2 liters at a temperature of 10 degrees Celsius. What would its volume be if I raise the temperature of the balloon to 20 degrees Celsius? Now you're saying, wait a second, I'm doubling my temperature from 10 to 20, so my volume should double, right? Because that's what it looks like. Because Celsius has that 0 in the wrong place, that's not what happens. Look what happens when we convert those temperatures to Kelvin, which is the correct scale to use for these calculations. Remember, to convert to Kelvin, we add 273.2. So 10 degrees Celsius is really a temperature of 283.2 kelvins. We add 273.2 to 20, and it's really 293.2 kelvins. Did our temperature really double? No, it went up very mildly. It only really went up by about 3%. So instead of seeing a huge doubling of our volume like we would expect looking at our Celsius scale, what we're really going to see in reality is when we use these Kelvin temperatures, is we're really going to see our volume increase by a puny 3% or so. So let's go over here to our formula and prove it. I have an initial volume of 2 liters. I have a final temperature of 293.2 Kelvin. I have an initial temperature of 283.2 Kelvin. And that's going to give me, what I'm going to do is I'm going to do it like this. 2 times 293.2 divided by 283.2 gives me 2.07 liters. So instead of seeing a dramatic doubling of our volume like we might think if we were looking at our Celsius scale, because that Celsius scale is deceptive with 0 in the wrong place, we're not seeing a doubling of our balloon. We're not seeing a doubling of our temperature. We're really only seeing about a 3% change. So that's why whenever you do calculations involving gases, you must use the Kelvin scale. So whenever you do your calculations, you must use the Kelvin scale. In today's lab, you're going to make a graph, and to make that graph, you have to do your temperatures in Kelvin. Now, your thermometer, I believe, your thermometer lets you record temperatures in Celsius. You have to convert them to Kelvin before you do your graph. I will give you a 0 for the lab if you don't convert your temperatures to Kelvin before you do your graph. The lab instructions tell you to do it. I'm telling you to do it. Let's work a couple examples of converting that temperature. If you have a temperature of 14.3 degrees Celsius, what's the temperature in Kelvin going to be? Your formula, write it down if you haven't already, is your Kelvin temperature equals your degrees Celsius plus 273.2. So 14.3 plus 273.2 equals 5.78. Kelvin. Let's try another. If we have a temperature of 101.9 degrees Celsius, what's our temperature in Kelvin? Pause it and see if you can work it yourself first. Did you pause me? Please tell me that you paused me. You didn't pause me, did you? You're just wanting to get this over with. Uncool. Major party foul. All right. I know, I've been going on a while, so I can't really say I blame you, actually. All right, so let's go ahead and do it. Our temperature in Kelvin equals our temperature in Celsius plus 273.2. So 101.9 plus 273.2. I'm going to use my calculator for this one. Nothing wrong with that. 101.9 plus 273.2 gives you 375.1 kelvins. One more example. You may, because you're using some ice water, wind up with a negative temperature. So let's say we have a temperature of a negative 19.6 degrees Celsius. What's our temperature in Kelvin? Well, remember our temperature in Kelvin is 273.2 plus our temperature in Celsius. So 273.2 plus a negative 19.6 degrees Celsius. Remember, adding a negative number is the same thing as subtracting. So 273.2 minus 19.6 gives me, again, I'm going to use my calculator here. Nothing wrong with using your calculator. I encourage you to use your calculator. No point in missing easy points. Gives you a temperature of 253.6 Kelvin. Chemistry's easy, life is hard. Why don't you write down for me one last thing here? Why don't you write down, we'll go Jacqueline Smith. Write down Jacqueline Smith. J-A-C-L-Y-N Smith. That's it.